looking at some conclusions that we can draw from this data. First, if I were to graph out my enthalpy of combustion versus the length of my carbon chain, what I'm going to see is I start out with a slightly sloping curve, but I'm steadily going to, actually it's going to slope the other way. I'm going to exaggerate this a little more so we can really see it. So we get a little bit of a curve, and then we have mostly a straight line. And that straight line is going to have a pretty constant slope, approaching the number 654. So with the exception of pentane here, the longer our carbon chain gets, the more we tend towards the number 654. The longer our carbon chain gets, the more we're just adding on a single CH2 molecule. And so I can effectively say that a CH2 molecule will use 654 kilojoules per mole, right? Kilojoules? Yeah, kilojoules. So when I get to something like C20H42, I can actually estimate that enthalpy of combustion pretty easily by just going, well, they approach 654 the longer the carbon chain. And so I can figure out the number of CH2s I'm going to have here on my C20H42, which is going to be 18. I can take 18 times 654 and get 11,772. And I could say 11,772. So I can estimate the enthalpy of combustion for pretty much any hydrocarbon. But this still informs me of that stability. Now, how does that inform me of stability? What do I mean by stability? Well, if we remember how reactions are going to occur, our reactions don't just magically happen. I don't have a CH4 molecule sitting next to a couple of oxygens and then all of a sudden just burst. It's going to happen as a collision, like head-on collisions on a freeway. It's happening at extremely fast speeds, extremely high velocities. And so I've actually got a molecule of O2 flying into this molecule of methane. And when they hit each other with sufficient force, they break those bonds and reform bonds into CO2 and H2O. So they reform those bonds. And so the longer my carbon chain is, you can kind of estimate this just by imagining it in 3 dimensions. The longer my carbon chain is, the more space I have for those O2s to hit. I also have more physical bonds that can be broken to release that energy. Okay? So the longer the carbon chain, we can say the more unstable it is. In our next section, we're going to be examining constitutional isomers of octane. As I've said before, I encourage you to use a ball and stick model to accurately represent this, to see this in 3 dimensions, to really see the concepts that we're getting at here. We're looking at the enthalpy of combustion of each of these isomers. So notice, octane has a chemical formula of C8H18. Now, if I make the first constitutional isomer, I'm making 2-methyl heptane. All I'm going to do is I'm going to take this methyl group off the end without breaking the whole thing, and I'm actually just replacing a hydrogen here. Putting that hydrogen back over right there. So notice, I haven't grabbed any new hydrogens. I haven't had to grab anything else. I just put this back together, and now it's only a 7-carbon chain with a methyl group on the 2-carbon. So this is still the same chemical formula. In fact, all of these are going to be that same chemical formula. But notice, our number of CH3 molecules goes up. In my first one, in octane, I've only got 2, my 2 end carbons. But in my 2-methyl heptane, I have 3 end carbons, and I can see that on this ball and stick model. I've got 1 CH3, 2 CH3, 3 CH3. So I can count my end carbons, and those will be a CH3 molecule. And so if we look at our enthalpy of combustion and look at our number of CH3s, which keeps increasing, the next one is 4, last one is 6, what is the relationship between the number of CH3s and the stability of that molecule? Make sure to graph this and then watch the next video for the overview.